We're going to do a little bit of work with exponentials and their functions and their inverse logarithms. Okay, so we have a little bit of notation here. If you have a natural number, a to the n means a multiplied together n times as such. So for example, a squared means a multiplied by a, and say a cubed means a multiplied by a multiplied by a, and I suppose a to the 1 just means a. Okay, and 3 to the 7 means 3 multiplied by 3 multiplied by 3 multiplied by 3, 3, 3, 3. Okay, so let's gather some basic properties of these powers. Okay, so we're going to just think at the moment this is just a notation, and we'll just ask some questions. What happens when you multiply together two powers? If you divide a power by another, what about a power of a power? These kind of things. So we're going to make this little golden rule here that when I talk about powers, I'm going to say like powers, which means they have the same base. So this number a here is the base. So for example, 3 to the 7 and 3 to the 11 are like powers. That's base 3. Whereas say 2 to the 6 and say 5 to the even 6, we're not really going to work with these things so much. Okay. I'll call this the golden rule of powers. Basically, all the laws that we're going to be using are more or less all for the same base. Okay, so let's have a look here. If we look at, say, 7 squared and 7 to the power of 3. So the question is, what happens when we multiply these together? So 7 squared multiplied by 7 to the power of 3. So what does 7 squared mean? It means 7 multiplied by 7. And what does 7 to the power of 3 mean? It means 7 multiplied by 7 multiplied by 7. And now we use associativity, which says when you have lots of things multiplied together, it doesn't really matter what order you do. And in fact, furthermore, you can change the order if you want. So this ultimately, however way you cut it, is 5 7s multiplied together. In particular, it's 2 7s plus 3 7s, in other words 5 7s multiplied together. Look, 5 7s multiplied together. Nothing special here about 7 squared, nothing special here about 7 cubed. So we have a general law where a is any real number and m and n are natural numbers, and at this point when I say natural numbers, I'm going to have to say that it starts at 1. Now we will eventually give meaning to the power of 0, etc., but at the moment, no. So we got a to the m. I'm going to draw the dot. That's just multiplied by a to the n is a to the power of m plus n. Okay, so if you try and do something similar for unlike powers, so say like 7 squared and 8 cubed, you'll see that you can't really get anything. That's why I use this golden rule. So a little just example here, write this as a power of 4. So there's kind of two ways we do it. So the first way is, well, just do the question as it is. So 4 multiplied by 4 multiplied by, and then note that 16 is 4 by 4. You don't really need the brackets. That's essentially what associativity means. You don't need the brackets. And what is this? This is 4 to the power of 4. And that's that. Alternatively, and we will eventually have to do this, we're going to kind of take an approach where, sorry, I just want to find a pencil, if I can find it quickly. So this is kind of the understanding, and then we're going to kind of use the rule. Now, you do whatever, but eventually we're going to get to a place where we're actually going to lean on the rule. Now, the mathematician will much prefer the understanding rather than using rules, but, well, we'll get there. Alternatively, we can say 4 is 4 to the power of 1, or even we could say maybe 4 by 4 is 4 to the power of 2. We could say that 16 is 4 squared, and then we'll use the rule that if you multiply together like powers, you add the powers. It's 4 to the power of 2 plus 2, which is equal to 4 to the power of 4. Okay. So adding like powers. Now you won't have to remember any of these. You will have the tables in front of you, but in my experience, you'll be far better off if you can do this without the tables. Like if you're going to try and learn this by tables, it's not really going to be great. Okay, next question. What happens when we do 10 to the power of 5 divided by 10 squared? Let's see what happens. So 10 to the power of 5 divided by 10 squared. Now there's one thing that we didn't go through in detail. I'm going to have to assume as understood that to multiply to multiply together fractions, you do top, top, bottom, bottom. And what that means also is if this is equal to this, this is equal to this. So that's going to be important in a moment, okay? So this is 10. Well, the way I'm going to write it is I'm going to write the 10 to the 5 as 10 cubed by 10 squared, and then divided by 10 squared. And then what I can do is I can write this as 10 cubed multiplied by 10 squared divided by 10 squared. Now if I want, I could put 10 cubed over a 1 to bring up with this, but really there's no real need. This is 10 cubed multiplied by 10 squared divided by 10 squared. Look, there it is, 10 cubed multiplied by 10 squared divided by 10 squared. So there's little bits of algebra that we're kind of assuming that you know, and the truth is people who've had issues with algebra up to now, and we show you the right way, they still have issues. So you might be in a little bit of difficulty in this chapter. Now, what's 10 squared divided by 10 squared? Well, the number divided by itself is 1. And what's any number multiplied by 1? Itself. So this is 10 cubed. Now, where does the 3 come from? Well, you have the 5 original 10s multiplied together, and then for each one on the top you can divide out one on the bottom, so it's 10 to the power of 5 minus 2. So the division of like fractions means subtraction of the powers. So again, there's nothing special here, so we're going to let a be a real number. We're going to specify something about a here. M bigger than n, we get that a to the power of m divided by a to the power of n is equal to a to the power of m minus n. Now, one thing we'll have to say is that we can't have a being 0, because 0 over 0, particular division by 0, is not defined. Because where is it? You can only do division if by a non-zero number. So I'm going to have to let, say, a in or without 0, or I could say a in or and not 0, something like that. Okay, so some examples. Write x to the power of 11 divided by x to the power of 5 as a single power. So one way is we just use the, basically we think it out again. So this would be x to the power of 6. This 11 x's multiplied together, just bunch them into 6 and 5. And then what you have is x to the 5 divided by x to the 5 is 1. 1 by x to the 6 is x to the 6. So that's thinking it out. And the alternative is that we don't really think at all and we just use the rule. In which case, this rule says if you divide like powers, you subtract the powers. So you get x to the power of 6. Yeah. So similar story here, writing this power of 10. So if we kind of just think it out, what are we getting? We're getting probably 10 squared by 10 to the 5. And 100 is the same. Well, maybe we recognize it here or not. So this is 100 is equal to 10 by 10. And then you divide above and below by 10 squared. So you get 1 by 10 to the 5, which is 10 to the 5. Alternatively, we use some rules which would say on top, multiply together like powers, you add the powers. Recognize that 100 is 10 squared. And then to divide like powers, you subtract the powers. So a mathematician would prefer this. This is more using the rules, but I'm going to get to a place that you're going to say, oh, you do actually have to have the rules, and we'll explain why eventually. What about repeated powers? So this is, remember so it's 9 cubed, that's 9 multiplied by 9 multiplied by 9 in the bracket. And it's to the power of 4, so it's 9 by 9 by 9, let me just write it down. So you got 9 by 9 by 9, by 9 by 9 by 9. So each of these are 9 cubed. And the power of 4 means there's 4 copies of them. The question is, how many 9s have you got? Well, it's 3 multiplied by 4, 12. So it turns out that, and again, there's nothing special here about the numbers. 9 could be any real number. 3 and 4 just have to be natural numbers. So repeated powers, you multiply the powers. Okay. So let's do a question here. So write 4 cubed to the 5 in the power in the form 2 to the power of n. So first of all, write the 4 as 2 by 2, 2 squared. So we'll separate kind of the rules and the thinking. So the thinking would go, okay, so you've got 2 squared cubed to the 5. And then this is after saying that 4 is 2 squared. That's probably what should have went. So I'll just write that over here. Just note 4 is equal to 2 squared. And now, so think about this. This is 2 inside here, 2 2's 3 times. So there's 6 2's multiplied together in there. And then think about this. So this is 6 2's multiplied together 5 times. So 6 plus 6 plus 6 plus 6 plus 6, there's 32's multiplied together. So that's the thinking way. And how about the rule way? So the rule way, you'd go here, repeated powers, multiply the powers. 2 by 3 is 6. Repeated powers, multiply the powers. I like this. If you can think like this, that's great. I think it's for the best. But we'll have to use the rules eventually, so it's not the end of the world to be thinking about the rules. We'll have to do it eventually. Okay, let's see this question. Express this as a power of 4. So now what we'll have to do is, probably with this, in fact it's not just x, it's x minus 3. Because this is an algebraic thing, we won't be able to think in the same way. Like I was visualizing here, say 6 2's multiplied together. I can't do that with x. So this is kind of the scenario where I have to just use the rules. Now we probably need to make, at this point, an assumption that x minus 3 is in the natural numbers, which in particular would say that x must be 4, 5, 6, etc. Now we're not going to specify which of those numbers that is. That's doing algebra essentially. Okay, so we note that 16 is 4 multiplied by 4, and 64 is 4 by 16, so it's 4 by 4 by 4, 4 cubed. So we'll write this thing out again. So you get 4 to the power of 4 there. 16 is 4 squared, and that's all to the power of x minus 3 divided by 64, which is 4 cubed. Okay, now probably what you want to do with fractions in general is think of kind of bold them having brackets around them, so you deal with the things on top first. Now that's not always going to be true, but it certainly works here. So what we're going to do here is, because there is shortcuts, we might do the shortcuts afterwards. Okay, so we have repeated powers, and as it's probably worth bringing in PEMDAS, which I'm actually going to start calling PEMA. Now, why am I getting rid of the D and the S? That is because division is multiplying by the inverse, and subtraction is adding. So that's why I leave those out. So here you've got an exponent, and here you've got a multiplication. You do the exponent first. So I'll do the repeated powers first down here. So I have 4 to the power of 4, and then 4 to the power of 2 multiplied by x minus 3. Now I'm going to write down something, 2 multiplied by x minus 3. I'm going to write it like that. Now this is not as written because of BEMA. Do the multiplication first. This is just multiplying x. So it's actually very important to show that bracket there, because it's you're multiplying a sum. And then divided by 4 cubed. I'm going to multiply this bit out. 4 to the power of 4. I probably don't have to do that, but I will. So 2x and then 2 by minus 3. I'm using distributivity. How do you multiply out a sum? And now multiplied together like powers, I add the powers. So 4 to the power of, now 4 plus 2x minus 6. So you've got 2x there, and you'd 4 minus 6, which is minus 2. And this is where now I've been using the rules the whole time here. I probably have to definitely use the rules here. I can't really think my way out of this. So I'm going to do the division of like powers means subtract the power. So 2x minus 2 minus 3, which is 4 to the power of 2x minus 5. I might have to check that a bit later. I'm a bit scubious about it. Alternatively, you could, if you're running not with rules, divide above and below by 4 cubed at the very start. So you can multiply above and below, or divide above and below by a number, because to divide you multiply by 1 over the inverse, and a number divided by itself is 1, so multiplying above and below like this is not, it's going to make it look different, but it's going to be actually the same quantity, and so the equals is justified. So I do 4 to the 4 divided by 4 cubed, so that's 4 4's multiplied together, and divide out 3 of them. You're just left with 4. And then this bit is going to stick here. Well, I suppose we'll multiply it out now. 4 to the power of 2x minus 6. And then 4 cubed divided by 4 cubed is 1. And so you've divided by 1, which is the same as multiplying by 1 over 1, which is the same as multiplying by 1, which does nothing. So I just leave it out. So this is kind of the really quick way of thinking your way through it. And then even I think here have to think of using the rules. So multiplying together like powers, I want to add the powers, and the 4 there is 4 to the power of 1. So even here, when we're kind of being smart and doing it as quick as possible, we do need the rules when you go somehow abstract. Okay. We've got some more stuff here. Okay. Now all of these are going to be collected the very back of the manual. I'll just have a look there, see do I have it. Yeah, this is, sure, I don't have to send to you, it's in the manual. Sorry. So all these things I'm going through are here, so you don't have to learn these. The way you think of, the way I would recommend, you don't learn off formulas like that. You just get used to them. So, like for me, I never learned these off. Now, obviously, I'm doing maths all the time. So, but that's how I learned them. I got used to them. But if you're stuck, you can look at that thing. So what about 2 by 5 to the power of 3? So this is 2 by 5 multiplied together by itself as such 3 times. Now, associativity means those brackets don't mean anything really. So like that's what associativity is basically saying. You can put the brackets wherever you want. So don't worry about the brackets. And then the other thing is we can change the order of multiplication. And so we can swap these, and you end up with 2 2's at the front. And then you can keep swapping the 2 out to get the 2 at the front. And when you get the 3 2's at the front, you've got the 3 5's at the back. You end up with 2 by 2 by 2, because you can swap, the order of multiplication doesn't matter, by 5 by 5 by 5. And if I want, I can put brackets around them, because that's associativity. This is 2 to the power of 3 by 2 to the power of 5. 5 to the power of 3. And there's nothing special about 2 and 5 there. So we have another general result that two things multiplied together to the power of n is equal to a to the n times b to the n. And that'll be, actually, I should keep that that little page nearby along with my axioms of the real numbers. So this actually, there's a question on functions that probably needs some of this stuff. It's probably worth commenting. Can I find it while I'm here? Probably worth. Oh, I don't have it. But there is yeah. I'll probably have to get back to that if I can remember it. Okay, so write this as a square. So it's two things multiplied together. So I suppose we'll work once again, kind of using our brains and just think how could you multiply two things together and get 4x squared? And you could just think of it, 2x by 2x, and you could swap the, so like if you wrote 2x, swap the x and the 2, you'd have 2 by 2 is 4, x by x is x squared, and you also have associativity of multiplication, which means that you can multiply in whatever order you want. And so this would work, because what is squaring? Two things, or something multiplied by itself. So that's one way. Alternatively, we kind of use this rule. I wouldn't be mad on this. So write the individual things as squares. So 4 is 2 squared, x is x squared, and then use this backwards. Because remember, equality works both ways. It's not like a programming equals. And so this is the same as 2x squared. I like this one, but you might need this one. All right, let's see an exam question. Now here it's looking for p being a rational number, but at the time of writing, we've only really done natural numbers. So we'll do it both ways. Now because the powers are whole numbers, although we got some algebra there with a, we should be able to actually figure this out, kind of thinking it out. So for example, when I see, so again we said if you're dealing with something like this, you should probably think of these. Now I'm going to do it the quickest possible way. Actually, sorry, what I'm going to do is I'm going to do the rule way first, and then I'll show you a quicker way. I don't really want you to do the quicker way because you're more likely, I want you to kind of do a mixture of the two, ideally. All right. So I do want to say that certainly when you're doing kind of thinking in terms of rules, you want to think about the top and the bottom as inside their own bracket, so deal with the top first. So multiplication of like powers, we know that we add the powers. So that will be 8 to the power of 7 plus 3 divided by 8 to the power of 2 all cubed. And we'll just tidy that up. Now I'm kind of overemphasizing the addition, but that's okay. Like really I should have just written 8 to the 10. Now division of like powers, you subtract the powers. So that's 8 to the power of 10 minus 2 cubed. And 10 minus 2 is 8, so 8 to the power of 8, all to the power of 3. And now repeated powers, you multiply the powers. So this is 8 to the power of 8 by 3, which is equal to 8 to the power of 24. So that's, now probably these bits here are unnecessary, but they're just really showing you what's going on. I can do it a bit quicker. So what I can do at the start is inside in this thing, I can multiply or divide above and below by a squared, because for similar reasons to what we saw on a different page, that will not change. It'll make it look different. So I'm going to multiply or divide above and below by a squared. So I'll get 8 to the power of 7, and then a cubed divided by a squared is a, and then on the bottom, now last time because I just left it blank, but look, a squared divided by a squared is equal to 1. And dividing by 1 is the same as multiplying by 1. And I'll just explain why that is the case. So dividing by 1 is the same as multiplying by 1 over 1. And what's any number divided by itself is just 1. So that's a little proof that dividing by 1 is the same as multiplying by 1. Part 3. So dividing by 1 is multiplying by 1. That makes no difference. How many a's have I got on top? I got 7 here, multiplied together, and 1 more, so that's 8. And now I'm thinking I've got 8 a's, 3 times 8 plus 8 plus 8. That's 24. So, yeah. Okay. Another similar case is a power of a fraction. Now, a work from the first chapter is not done here. But basically, it's just about how do you multiply fractions together. You do top, top, bottom, bottom. That's all I'm actually talking about. Okay. So, let's see how this works. So a over b power of n. Now there's different ways I can show this. Okay, so this means a over b multiplied by a over b multiplied by a over b n times. And then you just have to build it up. So top, bottom, bottom, you get a squared over b squared. Then into the next one, you'll have a squared by a, b squared by b, you'll have a cubed over b cubed, and keep on going till you run out, and you'll end up with a to the n divided by b to the n, and that's also one of our little rulinios. So something like this. Okay, so that is the basics of powers, and now what we're going to do is we're going to use those rules. So the 3 rules, the fundamental rules here are these 3. What we're going to do is we're going to use these 3. We're going to take these as axioms, if you will, and use them to define zero powers, negative powers, and fraction powers. And then, yeah, things are a bit more difficult then if you want to do real number powers, like the power of square root of 2. We won't be worrying about that.